of resistance to first-line medically important antimicrobials, tetracyclines, sulfonamides, penicillins, and quinolones. But then also for Vibrio and for Aeromonas in particular, moderate to high rates of resistance to carbapenems and polymyxins. Across all subregions, mean E. coli resistance to third-generation cephalosporins was 27%. I think that aligns with some of the data that was just recently presented. And then across all gram-negative pathogens in the study, callistin resistance was 41%. And then this, I'm sorry, I don't have a pointer, but the bottom right panel here is Aeromonas from southern and western Asia. And here we find very high rates of resistance to carbapenems. Mean resistance was 40%. And also the third and fourth generation cephalosporins, where mean resistance was almost 70%. So I think this is important for two reasons. One, it signals an erosion of therapeutic options for invasive, non-self-limiting infections from these pathogens, but also, and I think this was, Dr. Wuntic just talked about this, is the horizontal gene transmission. So for those resistance that are mobile in nature, the possibility of horizontal gene transmission between bacterial genera in the aquatic environment. Next slide, please. So then we mapped AMR, as I mentioned, both in freshwater and in marine environments. And essentially we use an ensemble modeling technique in which we train multiple child models with environmental and social covariates, and then we stack those models and use the predictions in the final map of freshwater AMR. And we see that AMR is higher, over 50% P50 in the Great River systems of Asia, in particular the Yangtze River, both its upper reaches and then its Huayang Lake. And then the Mekong region, particularly its delta in southern Cambodia and Vietnam, also in southern India and in eastern Turkey. And then lower rates of multi-drug resistance in peri-urban Guangdong, Guangzhou province, southern China, and then also in Japan and Korea, although I would note that that lower P50 in Japan and Korea is associated with high uncertainty. Those countries contributed relatively fewer point prevalence surveys to the study. Next slide, please. We also asked, given some of this uncertainty, where would we want to prioritize future surveys to fill in gaps in knowledge around antimicrobial resistance from aquatic animals in the freshwater environment. So we use a background rate of uncertainty that we weight according to human population density and also freshwater aquaculture production. And we do that because we're interested in knowing where we should prioritize those studies where resistance is likely to have the highest impact, both on human health and also on the aquaculture industry. And then we use a byproduct, essentially, of the modeling technique that reduces uncertainty with the placement of each additional survey. And we find that surveys should be prioritized largely to China, both eastern and central China, to India, western, central India, and also India and Nepal border along the Indo-Gangetic Plain, and then also to Indonesia. Next slide, please. So finally, mapping of AMR in aquatic animals from coastal environments. And here we also apply the transparency function to pull out, essentially, those areas with higher relative survey density. And we find that AMR is high, with P50s greater than 50% along coastal China, in particular in the north, but also in the south, along Hainan Island, which is an area that's poised for substantial expansion of coastal marine aquaculture. Also along coastal Vietnam and in the Bay of Bengal between southern India and Sri Lanka. And then lower rates of P50, less than 10%, along coastal Thailand and Malaysia, both the Gulf of Thailand and the Indian Sea. Next slide. Okay, this is my final slide. Just a few sort of conclusions and policy implications. I think one, what really stands out is urgently the need for better evidence compared with AMR data from terrestrial animal production industry and humans. There's really very, very scant evidence from aquatic animals. And we need that to both better understand the emerging trends and also to target interventions where they'll be most effective. We also need to establish both AMU and AMR monitoring systems in these animals, in particular longitudinal surveillance focused on antimicrobial resistance in aquatic animals entering into the human food supply. And I think embedding that in interventional action plans to codify it and have a degree of sustainability is an important component of that. But we don't need to wait for that data to come online. That sometimes takes years to happen. And so I think right now we know that we can work to incentivize on-farm biosecurity, improve husbandry and management on farm, improve vaccination rates for vaccine-preventable diseases, all of which will reduce antimicrobial use on farm. And then, and I think Dr. Wartenau spoke about this earlier, connecting AMR across the food chain and understanding through systems like the ESBL, the Tricycle Project, how, for example, resistance may be moving from aquatic animals in the aquatic department into human clinical settings. So I'll stop there. Thank you very much. I think the last slide, all of this data is publicly available for anybody that wants to see it. Just the last slide, please. Yeah, this is event.org. Thank you very much.
Thank you very much, Daniel. เพื่อเป็นการไม่เสียเวลานะครับผมขอเชิญผู้ที่มาท่านถัดไปนะครับเป็นคุณโชคดีเป็นกิจผลนะครับคุณโชคดีเป็นโปรแกรม Manager on Food System ของ World Animal Protection Thailand นะครับระหว่างที่เราคุณโชคดีเดินขึ้นเวทีนะครับผมขอแจ้ง2อย่างนะครับอย่างที่1คือขอแจ้งกับทางผู้จัดนะครับว่าเดี๋ยวเราจะมี question and answer แล้วนะครับเพราะว่าเดี๋ยวเราจะได้จบแล้วเบรกได้เลยอย่างที่2คือผมคิดว่าอันนี้เป็นอันสุดท้ายของเซสชันนี้ก็จริงแล้วเราเหลือเวลาเที่ยงพอสมควรแล้วแต่ก็อยากขอให้ทุกคนอยู่ด้วยกันก่อนนะครับเพราะว่าทั้งทางห้องแล้วก็ทั้งทางออนไลน์ด้วยนะครับเพราะว่า